Hello, everyone. We're going to wait for the crowd to settle here. I'm Ed Pegg Jr., and I'll be repeating myself over the next minute, most likely. All right. Okay, we've got some people visiting us. Okay. Welcome to the 6th episode of Mathematical Games. Today I'll be talking about sparse rulers, Golomb rulers, different sets, and other related items. And this is part of a series I'm doing in homage to Martin Gardner, who ran Mathematical Games for Scientific American. I'm trying to do some talks in sort of the style of what he did, where we're pushing the boundaries of what's known in recreational mathematics. And in the course of making this talk, I managed to push a few boundaries. So let's review what we're going to be talking about. What is a sparse ruler? So here's an example. It's a ruler with 6 marks, and it can measure all of the distances from 1 to 12. For example, from 0 to 1, that measures a distance of 1. 0 to 2 measures a distance of 2. 6 to 9 measures a distance of 3. And this is the minimal number of marks that can measure everything from 1 to 12. You can't do it with fewer marks. And one of the questions from the 1930s was, what is the minimal number of marks for a general length? And it turns out that it's this formula, the XSN, or the number of marks, is equal to this with some excess. And e to the e sub n is always 0 or 1 for all n. And this funny bracketing here, that means the round function. So here are a few sparse rulers here. And here's a larger ruler. Here's a ruler of length 214. Here's the marks in it. And this is my favorite of the sparse rulers. I call this my 1 meter ruler because it has a gap in it of 100 centimeters. And I've got some copies of this, where I basically just marked these places on a normal fiberglass measuring tape, and you get this nice sequence. And it's pretty easy to pick out the sets of marks you need to measure a given distance, just because everything is so regular. And we can check that this works if we set the number of marks here and we tally all the differences. We get that all the differences 1 to 214 are covered somewhere within these sets of marks. So that's a sparse ruler. All differences must be covered, but they can be repeated. You can see some, like for 102, there's 2 different ways of measuring 102. There's 7 ways of measuring 1. And there's various ways of measuring 3. A Golomb ruler, differences can be missed, but nothing can be repeated. So if we do the same thing with this Golomb ruler of length 216, you'll see that everything here ends with a 1 when we tally all the possible differences. There's only 1 representation for each distance. And it turns out that the length of 91 cannot be measured by this Golomb ruler. Neither can 93 or any of these other measurements. With the Golomb ruler, you miss distances but nothing's repeated. With the sparse ruler, you cover all differences, but some are repeated. If you go modular, you get what's something called a difference set. For example, here is a difference set. There's only 3 points in it, mod 7. 0, 1, 3 is an example of a mod 7 difference set. And so from 0 to 1, you have this one arc. From 1 to 3, it's a difference of 2, but it's modular. So you could go either direction for your differences. And there are differences, different sets known of various size. And in this demonstration on different sets, you basically give, I give the arcs for every single possible set of modular differences. With a difference set, for example, this is a difference set Springer found, James Springer in 1938. We can look at all the possible differences modulo 183, and we get that everything is represented exactly once. And we can check that if we do this bit of math and look at the comparison, it's exactly equal to range 182. So it's all the differences 1 to 182. So those are the 3 major types here. If you use modularity, you can cover all distances uniquely with a Golomb ruler. You can avoid repeating anything, but you'll wind up missing things. And with a different set, you cover everything, but things can be repeated. So here's a bit of history on the problem. Sparse rulers were looked at under a different name originally, and Paul Erdos managed to prove that a limit exists for the number of marks based on the square root of the length. And I think we can show this here. Let's see here. Here's Erdos' problem, number 170, the sparse ruler problem. This is at erdosproblems.com. In 1956, John Leach managed to come up with bounds. John Leach is the same mathematician who did the Leach lattice. In 63, Brian Wickman came up with a paper, which will be discussed later, and he's now credited for having solved this problem. He was able to find this upper bound of square root of 3 almost in his 1963 paper. I managed to make a trivial addition to it so that he wound up getting credit. Let's see. In 1967, Robinson and Bernstein predicted the best 24-mark Golomb ruler, and then they, in 1984, predictions were made for Golomb rulers under 100 marks, and we'll be getting to that. In 2014, Distributed.net did a giant computer search and managed to prove that the 24-mark Golomb ruler was correct using tens of thousands of hours of computer time. And also the same year, Archie Robinson verified sparse rulers up to 25 marks using another big system. He worked for Intel. He was given access to about 600 Intel processors, and with those, he was able to compute sparse rulers up to length 213. In 2016, Thomas Rokicki and Dogon made predictions for the best Golomb rulers with under 40,000 marks. So that's a list at cube20.net. I think that's it. And I managed to come up with the Sparse Ruler formula in 2020, which basically proved this. And just last year, distributed.net verified the 28 mark Golomb ruler. So I'll be getting to all of these. Let's get to a few more sparse rulers. So here's a sample case, the sparse ruler of length 13. And if there is only 5 marks, you could only do 10 distances. So that's not enough. But with 6 marks, you can get 15 differences. So that might be enough. And we can check that this set with 6 marks actually does cover everything. Here's difference 1, difference 2, 3, 4, all the way up to difference 13. And we can check this in various different ways. So for length 13, you need 6 marks, and that's easily provable. For length 50, it's non-trivial to prove that 12 marks is minimal. You pretty much need to do a brute force search, which is what I've already forgotten his name, which is what Arch D. Robinson did in 2014. So here's a visualization of this ruler showing how each difference from 1 to 50 is measured with this set of marks. We could also show that ruler as this set of marks here. The differences between the marks is this pattern here. 1, 2, 3, a bunch of 7s, 2 4s, and a 1. Well, we could represent that in what's called the split form. 1, 2, and 3 each occur once. 7 occurs 5 times. 4 occurs twice, and 1 occurs once. This sort of representation is very useful for sparse rulers because it's really pervasive how often these numbers repeat. So I could show you a sparse ruler of length of Google 10 to the 100, and it's basically in this form. It fits nicely within about 3 lines. If we weren't allowed to repeat the numbers, it would of course fill a large book for the case for a Google. So for where are we? Okay. Brian Wickman was the one who kind of cracked the problem. And this is the recipe he used, and this is for that split form I was just showing. So for example, this recipe gives the ruler we were just looking at. If we plug in 1 and 5, we get that split form we were just seeing. 1, 2, and 3 once, 7 5 times, 4 twice, and 1 once. A related recipe, what I call W2, is here. It's very similar to Wickman recipe number 1 up here. I believe this, where is it? Right, here it's 1 plus R, here it's just R. And that 1 plus R moves to over here. So basically we're moving 1 mark for the second Wickman recipe. And it turns out that causes the length of the ruler to be 1 less. So we can set up a whole bunch of these Wickman recipes and see what they do. So here's a rundown again. We've got the ruler form, which is just the marks. The differences form, which is a list of the differences between the values, and the split form, where the number of repeats for each number is given. And if a number is repeated more than once in sections, you just basically start the count over again. And here's various pieces of code to convert back and forth between these forms. for ruler 50, we can basically do this, and that gives the split form, and it returns the differences form. And if we do the differences on that, we get back and forth. And this is basically just showing the various ways of getting back and forth. And here's a table showing the original recipe. Here's the recipe down here. If we plug R equals 1 and S equals 5 into these, we get these values. So basically, this isn't actual exponentiation. This is basically we're basically 7 is repeating 5 times. 1 occurs once, 2 occurs once, 3 occurs once, 7 occurs 5 times, 4 occurs twice, 1 occurs 1 time. So we can make larger rulers making this recipe. So here's the one I've been showing, length 50. And if you plug in the various values here for R and S, you get these rulers here. For example, for 213, 19 occurs 6 times in a row, then 10 5 times in a row. Here is the last known ruler, which is both optimal but not a Wickman ruler. It has length 58, and it's predicted that this is the last non-Wickman optimal ruler. It has 13 marks, and there it is. It's a somewhat unusual construction. And I believe that this is the last one. I'm not sure of that, though, and I have no way of proving it. We do know that this is the last one up until length 213, because there's been a brute force search up to that. So in 2018, I got involved in the problem. And basically, I just wanted to use the data that Robinson collected because I read about it. So I wrote to him, and he said, "Oops, I accidentally lost all the data." So basically, there was nothing left of his big run, except for a few sequences in the online encyclopedia of integer sequences. So basically, we knew what a few answers were, but we didn't actually know what the sparse rulers were. And the number of marks, this is what it looks like up to 214. It starts to wiggle at 130, and no one knew what was going on here with this sequence. I was able to use Wickman rulers to reverse engineer this as a formula. And it seemed like we can boil down all the solutions that Robinson found into a series of zeros and ones using this formula. And there's the series here. You've got 50 zeros in a row, and then a 1, and then more zeros and a 1. And it was just a puzzling sequence. And when I extended on with more best known results, I tried making various rectangles with it, but it didn't seem to make any sense until I decided to look at the best known rulers at each case and set those as a floor value. And that's when we got this pattern. Everything started nicely clumping together. Here are the unusual cases where the wriggles were. And there are various odd values at the top. These values up here at the top, we probably could have modified this formula to make these go to 0 instead. But this was a really simple formula, and these were always just going to be 1. So I figured it's best just to keep the formula simple. And this looked like a really good way of seeing the data. I showed this to N.J. Sloan, and he called this pattern dark mills on a cloudy day when he saw this. We extended this to 10,000, and this is the weird pattern that formed. And this area down here is what Dr. Sloan called the dark mills. And up here, there's various places where it was also one. The excess here, excess is a number of marks minus 3 times the length plus 9/4, square root and rounded. Unusual little formula. And we got this, that's long series of zeros and ones. And this is what happened when we plotted out those zeros and ones. And pretty much from the moment this image was produced, the problem has been sort of considered understood, because everybody that looks at this for more than a few minutes basically sees, yeah, there's a pattern there of some sort. There's probably lots wrong in this pattern, but it's pretty accepted that something like this pattern is true. So we can take a look at why this problem is really difficult by looking at unique cases. For example, length 88 is only findable with a computer search. Here's the solution for 88, and it's unique. Ruler 110 is also unique, and that's what it looks like. Let's see. Here's some more of the unique ones. I'm showing them in the split form. These rules at the bottom here past 178, these probably aren't actually unique. I just don't have a computer sufficiently powerful enough to find them. And it's possible that no computer or system in the world is powerful enough to solve, say, 334. That might be doable. And if we went with all the computers in the world, we might be able to do this case. I'm not sure, though. Actually, distributed.net managed to solve length 585 for Golomb rulers in 4 years on thousands of computers. So I might be wrong, but it's so this one probably is able to be looked at, but it would be a whole much of work for solving a small problem. So there's also some very difficult solutions to find. This was the really hard one here for me. I wanted to show that the excess was always 0 or 1 for all sparse rulers, but 1792 was a particularly difficult one to solve. But I finally managed to solve it on an old system that I had running for months, and it finally spit out an answer. There's various sequences for OEIS for this. We can take a look at one of them here. Here's the one that has lots of data on it. And if you go to this bottom link, these are basically example rulers for all lengths up to 10,000. And the number of marks is given, the length is given, and the excess is given, plus a representation of the split form. So once I had a whole bunch of different Wickman recipes, I managed to find about 800 different ones. I started making different recipes, and this is the original recipe here. We can basically vary R and S. And if the red dot is in the white here, you basically get a ruler that has an excess of 0. If it's in black, it has an excess of 1. So here are the, this is a demonstration, Wickman-like rulers. It's on the demonstration project. You can basically play with these different recipes. So for example, here's recipe number 9. It uses this set of values, and you can, this is what the ruler looks like for those R and S. And here, over here is the split form of that ruler. And we can keep on going here. All these different recipes are quite similar to each other, but they have obvious differences. And I still don't know how to find more of these recipes. What I'd like to do is find 3 variable recipes, RST. One recipe I know of is adding a T value at the end of one of these items here. I used Wickman recipe number 1 and just added a T value at the end, which was the size of a size less than R. And with that, I could basically just add 1 mark, but cover a whole bunch of extra differences for a ruler with only an excess of 1. And that was enough to prove the square root of 3 bound for the Erdos problem. Since I basically just added 1 mark to Wickman's problem, that was considered a trivial addition, so Wickman got credit for solving the Erdos problem. Here are a whole bunch of different sparse rulers. We can, this is another demonstration. We can basically, oops, not sure why that happened. Oh, let's skip that one. But this is a demonstration that works better outside of a slideshow. And hopefully I'm not going to crash here. It wants to format things. Okay, anytime. I might need to restart my talk here. All right, let's see. I'm trying to get my notebook back here. And I'm going to open up in a different version of Mathematica. All right. Just 1 moment. All right. Okay. Sorry about that. Okay. Oops. So for some reason, that one didn't want to cooperate. So with the Wickman recipe, we can just add a single mark, and that's what I'm doing in this demonstration called Wickman columns. And We can basically pick the number of marks, say 800 marks. So that gives rulers of length 213,000 plus x. So for x in any of these values, we get items that work. The red indicates that a sparse ruler cannot be generated, and blue indicates a ruler with excess 0, green indicates a ruler with excess 1. And I forget where, but after a certain length, for example, here's some ones that don't work. For 433 marks, these values cannot be covered just by adding an extra mark. But for anything over about 800, everything always worked. So basically for rulers under a length of 1,000,000, there's some problems that need to be solved. But for everything greater than 1,000,000, just using the Wickman recipe and adding a single mark solves everything. So basically it turns out for this problem, it's a rare case, the big values were easy to solve. It was the small values that caused problems. So that led to my proof of sparse rulers, which is basically big values are easy. Here's solutions for all the small values, and done. And I gave that proof in much gorier detail in a blog post a few years back in 2020, right before the pandemic hit. You just look in our blog and you can see the full proof. So one thing I didn't cover in the proof is whether the excess value can be -1. We haven't been able to prove that's impossible, but it seems highly unlikely. And if such a ruler exists, it has a length of greater than 213. Each of these solutions, when they're really good, it causes a big splash. Basically, for every excess 0 solution, I was able to do some tweaks on it to get thousands of other solutions. And if a super ruler with this occurred, basically it would leave a big mark in the solution space. And I did a large search in the solution space, finding millions of these sparse rulers, and there was no evidence that anything was causing a splash of that magnitude. So here's a few examples. So here's length 58 is the last known non-Wickman optimal ruler. Here's the last ruler with just 3 differences, 1, 9, and 8. Here's the last one where the greatest difference between values is 12 at 181. Here's the last one with just 4 differences. Everything is either 1, 62, 4, or 5. Here's the last one where only 5 differences are used and in the split form, and basically half the ruler is right there. Here's the last one without consecutive repeats. And here's the last known with a large gap, greater than 1/3 the length. And this 582 is what's called a cloud value. So let's switch to Golomb rulers. In 1938, James Singer developed a method for finding different sets and Golomb rulers using generalized Fibonacci sequences. So here's an example of one. Let's say no. So here's a generalized Fibonacci sequence with 1, 3, 0, 1, this linear occurrence. And if we take the mod values, we get various values of 0 to 4. And we can partition this 0, 1, and if we sort them, we get basically all the pairs 0 00 or 01 to the 44 here, except for the first one, 00. If we don't sort these, we get this 01, 11, 14, and so on. So where does each of these coordinates occur in a zero in a 5x5 grid? Well, we can find that, and with map indexed, we basically get this sequence, which we can put into a grid. 00 is skipped, and for any pair here that is maximally Fibonacci, such as these, we can get this grid which has rows and columns. Well, it turns out that each of these rows and columns is a Golomb ruler with no repeats. And I show them up here with the marks. And that is something we can do for any prime. For example, here's prime 23, makes this big grid, and every single one of these rows and columns is a Golomb ruler. This is what James Springer found back in 1938. He used this method to generate these sets, and he was mostly looking for what's called difference sets, because these work as in a modular way. And this is how he developed the Springer difference sets. So basically no differences repeat due to a peculiarity in how generalized Fibonacci number works and for prime values. So this is basically either an affine plane or projective plane based on how you approach the problem. And Thomas Rukiki at cube20.org used this method to extend it out to a lot of marks. I think he went up to 500,000. And one thing he found was that prime gaps can mess up how the projective geometry and affine geometry works. And it turns out that for this particular number of marks, 42,116 marks, that the Springer method completely fails. It's unknown how to make a Golomb ruler with that many marks. However, since we're only up to 29 marks for what's been verified true, we probably are never going to get to solving this particular problem. But the toolbox that we use, the Springer method that's been used since the 30s, won't be applicable for that particular number of marks, which I found quite interesting. And this is another demonstration. Here's the name of it up here again. Golomb rulers and Fibonacci sequences. You just basically make the generalized Fibonacci sequence, you pick your prime, and you get a whole bunch of possible Golomb rulers. Now, they may not be minimal, but they won't repeat any differences. So let's take a look at all the cases involving 11. So for 11, these are the pairs in a linear recurrence that are maximal, that'll hit all 120 values. So if we pick one of these, this is the grid that gets generated. And let's see, the last one, this is what 7-9 generates. So each one of these generates a whole bunch of rows and columns, and we can look at all the rows and columns generated for each one, and then also take a look at since they're modular, do all the various rotations. And it turns out if you look at all those, the shortest Golomb ruler that comes out of that is this one here. It has length 34. Well, it turns out that best Golomb rulers found with a computer search have a length 32. So this is one case where the Springer method did not work. It was a computer search that found it. However, there's only 8 known occurrences where the Springer method did not work. In all of these searches, nothing in the past 20 years has been something new. Here's all the known Golomb rulers that have been proven. There's only 37 of them. Here's the last one that was found last November. We can sort these in various ways. This is going to be a new demonstration sometime soon. It'll be called Golomb rulers. Just watch the demonstration site. So each one of these basically shows the various places, the various differences that could be found. But some are missing. For example, for length 17 and 6 marks, these are gaps in what's representable. And I'm not sure which 8 of these are not found with the Springer method. That's something I should probably mark in this. But all the larger ones were found with the Springer method much earlier. These Golomb rulers are also called side-on sets. If you take any Golomb ruler and add up the values, all the sums are distinct. So for example, with this particular set, if we do all the possible sums, we get this list, and none of these are repeated. It turns out that every Golomb ruler is a side-on set, and every side-on set is a Golomb ruler. And it's easy to prove that. Basically, if there was a case that you had a Golomb ruler that did not generate a side-on set, then you could take 2 values in that side-on set that represented a repeat. And then so that's say A plus B is equal to C plus D. Well, then you just use a little bit of arithmetic. A minus C is equal to B minus D, but that would indicate that the Golomb ruler had a repeat in it. And because of that, that's not possible. Therefore, all Golomb rulers are side-on sets, and all side-on sets are Golomb rulers. We can extend this to 2 dimensions. For example, if you're given a number of points, how close can they be so that no distance repeats? Well, it turns out this was an Al Zimmerman contest problem, and here are all the best known solutions up to how many points? 26 points. And it's believed that due to the amount of computer power devoted to this during the contest, that these are the minimal solutions. And this is another demonstration, no repeated distances demonstration. What about covering all differences? Well, this is a new demonstration that will be published next week. This is sort of the 2D equivalent to sparse rulers. You have to cover all differences, but it's possible to repeat. So for example, when there's more than one green line, that means that, for example, here, that means that that distance of square root of 26 repeats with this set of points. We've managed to solve this up to a 10 by 10 grid. There's a search going on for the 11 by 11 grid right now. But so far, for all solutions 5 to 10, the minimal solution needs n plus 2 points. Whether that will continue on, we don't know. This is an unsolved problem. Oops. So these are examples of that problem. Let's see, at the community site here, this last number 2663076, I give data for 3 million sparse rulers. And you can look it up here, and if anybody plays with it and manages to find more sparse rulers, I'd be very interested in seeing what the results are. I tried all sorts of computer methods to take a solution and find more solutions, but maybe there are some new methods that could be developed. So in there, you can see various things like, here's a whole bunch of length 214 rulers. And here's a extension to the dark Mills pattern. Everything is proven up to 213. This is what it looks like one block after 213. These values here, 226, 244, 262, 300, those are all highly suspect values. It's likely that one of those four, the solution is actually excess 0 instead of excess 1. It's just that my computer search wasn't sufficiently powerful enough to find whether or not those were the minimals. I'm pretty sure one of those four is wrong. So let's see. Here's some other problems that are unsolved. What about 3 dimensions? How close can points be without repeated distances in a 3D grid? That's not been looked at so far as I know. What's the minimal number of points to cover all distances in a 3D grid? Well, the 2D grid is something that was just looked at this week, so I'm pretty sure the 3D grid has not been looked at either. What about other lattices like the octahedron, tetrahedron lattice and similar things? What are the minimal cases in those? Just for in 2D, a simple triangular grid, what is the minimal sets of points in those? Those are all unsolved problems, and that is what I had prepared, so I'll be glad to answer any questions. You can just post them and I'll be glad to take a look at them. Let me see here. Oh, and my other screen finally resolved. Let me close that. All right. Tilings. For example, in tilings, a conference room can be set up with Golomb ruler partitions. And with that minimal set of partitions, you can basically throw up 2 partitions so that the conference room is of any desired size. And there are some hotels that do that, use Golomb ruler partitioning for how they split up their rooms. So that's one tiling application for at least Golomb rulers. Sparse rulers would work better for partitioning though, because they can cover all sizes, whereas Golomb rulers miss things. Any other questions? All right, many thanks. I look forward to seeing everybody again next month, where I'll have something figured out for the next talk. Many thanks, everyone.